Alright, so in today's video, we're diving deep into one of the most fundamental reactions in organic chemistry, nucleophilic acyl substitution. This reaction is essential for understanding the chemistry of carboxylic acid derivatives like anhydrides, esters, and amides. We'll break down the mechanism step by step, explore how these molecules react, and cover examples such as anhydride cleavage, transesterification, and amide hydrolysis. If you're preparing for the MCAT or building your organic chemistry knowledge, this video will give you a comprehensive understanding. Let's start by explaining nucleophilic acyl substitution. The reaction begins when a nucleophile attacks the carbonyl carbon of a carboxylic acid derivative, displacing a leaving group. Carboxylic acid derivatives react at different rates. Their reactivity order is anhydrides, most reactive, esters, moderately reactive, amides, least reactive. This trend is influenced by the stability of the leaving group and electron withdrawing effects. Let's break this down with specific examples. In anhydride cleavage, a nucleophile attacks the carbonyl carbon of the anhydride, breaking the molecule into two parts. Anhydrides are highly reactive due to their structure, which contains two adjacent carbonyl groups, making them more electrophilic. For example, when ammonia reacts with an anhydride, the nucleophile attacks one of the carbonyl carbons, forming an amide and a carboxylic acid. The carbonyl carbon serves as the electrophile, and the carboxylic acid acts as the leaving group. When an alcohol attacks an anhydride, the products are an ester and a carboxylic acid. This reaction is efficient because the anhydride's high reactivity ensures that the nucleophilic attack proceeds quickly. When anhydrides are exposed to water, they undergo hydrolysis, forming two carboxylic acids. This reaction follows the same nucleophilic acyl substitution pattern, where water acts as the nucleophile. If the anhydride is symmetric, you'll get two identical carboxylic acids. However, an asymmetric anhydride produces two different carboxylic acids. Now, let's talk about transesterification, where one ester is transformed into another by exchanging its alcohol group. The mechanism involves an alcohol nucleophile attacking the carbonyl carbon of an ester, displacing the original ester group. For example, when methyl acetate reacts with ethanol, the products are ethyl acetate and methanol. This reaction is common in organic synthesis when modifying ester groups in large molecules. Finally, let's look at amide hydrolysis. Amides are the least reactive carboxylic acid derivatives, so hydrolysis requires more extreme conditions, either acidic or basic. In acidic conditions, the carbonyl oxygen is protonated, making the carbonyl carbon more electrophilic and susceptible to nucleophilic attack by water. The products are a carboxylic acid and ammonia. Under basic conditions, a hydroxide ion directly attacks the carbonyl carbon. Instead of forming a carboxylic acid, you get a carboxylate ion. Let's recap the key reactions. Anhydride cleavage. Anhydrides react with nucleophiles like ammonia or alcohols to form amides, esters, and carboxylic acids. Transesterification. Alcohols replace the ester group in esters, swapping one alcohol for another. Hydrolysis of amides. Amides require acidic or basic conditions for hydrolysis, yielding carboxylic acids or carboxylate ions and ammonia. Each of these reactions follows the general mechanism of nucleophilic acyl substitution, where a nucleophile attacks the carbonyl carbon, displacing a leaving group. If you found this breakdown of nucleophilic acyl substitution reactions helpful, don't forget to like, subscribe, and share. For more in-depth interactive content and study resources, check out King of the Curve. Thanks for watching, and good luck with your studies.